Hello, people. Let's see. Making Templeton a co-host. Yes. All right. No doubt. Templeton, how was the skiing? Templeton, he skins up. He goes to those places that you see out in the middle of nowhere. He does. When was the last time you were on a ski lift, Templeton?
Maybe a couple, 3 years ago. Can you hear me?
All over the place. Yes, there it is. Someone sound off, and can you hear me? Cool. All right. Thank you. Let's see. Big stuff today. All right. Big stuff number one. We'll answer your questions on the quiz. I posted the key yesterday morning, really early, like, I don't know, 5:30 in the morning or whatever. Crazy, right? So we'll do that first. We do have some new stuff to go over today. Differential equations. Big word there, big phrase, differential equations. And then we got to talk about the AP test, because the College Board came out with some stuff over, I think they announced it on Friday. And there's some clarity now on what the heck is going on. Okay, so later on in our class, we'll get to what the heck is going on with the AP exam. And yeah, and just to give you a little hint, you'll be taking it at home. What? Taking it at home? How is that possible? So I know now you're going to stay. Some of you are going to bolt here in about 5 minutes, but now you're going to stay because you want to hear how in the heck are we going to do this at home, right? Okay, so that's our three-pronged day. Go over the quiz, take a look at the new stuff, differential equations, and then finally talk about the AP test, which is kind of cool to have at least some idea of what's going to be happening. Okay, so here we go. So I'll get rid of this. So those of you that access the key, hopefully that was helpful in being able to, I'm admitting some people. That was helpful in kind of looking at what you did. And it seemed to me, and again, I wasn't doing it, it seemed to me that the Google Docs worked okay. I don't know if there's a better way to do it, but it seemed like, you know, I got what I get from the Google Doc is I get a kind of transcript when you guys are doing, I don't know if it's a Google chat or whatever you're doing, but I get some information about how you're communicating with each other, et cetera, et cetera. And it looked like there was some good, solid, you know, collaboration going on about, you know, and some good explanations, et cetera, et cetera. And then also it looked like some of you did some Zoom meetings. All right, that was pretty cool. And just FYI, I mean, if there are more people, if there's more need later on to do some more collaborating, it looked like a lot of you set up Zoom meetings that had, so you needed a password. You can set up a Zoom meeting where you don't need a password, because obviously you got in without a password, right? And so you can set it up so all they need is a link. That's kind of good to know. Oh, one more thing, the recordings. So I used to have some hair left. Yeah, I lost a lot of it because I'm pulling it out because of the recording thing. This is funny. So last Tuesday, last Tuesday, long time ago, I recorded to the cloud. which is one of the options. I knew I'd have to stop doing that, but I recorded the cloud, and it took, I mean, Zoom is so busy right now. It took until Friday. Okay, so again, I recorded on Tuesday of last week, St. Patrick's Day, right? And then it took until Friday afternoon for it to be fully processed. That's how busy the Zoom website is. Yeah, crazy, right? That being said, the website hasn't crashed, right? I mean, it takes a long time for them to process the videos. And so, but it hasn't crashed, right? Which is really awesome that they have enough infrastructure built up that with all this extra demand and use that they're still okay. With the recordings though, I'm having to record locally. And so those files are like 1.2 gigs. And so Schoology does not let me upload or post something that large. And so I'm looking for multiple workarounds. I mean, I even started a YouTube channel, blah, 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 but you know, I can't upload it because, you know, it goes to about 50% uploaded, then goes back down to 2% again. Like what? And so I'm working with the district for workarounds. So thank you for being patient with my videos and not them, the recordings, they're not being posted. That's just me. That's just my way of getting you to come to class. Right. No, that's just your way of being a hack, Mr. Kuhn, and ineffective. Okay, so let's talk about the quiz. Okay, so I saw 11, 12, 13. Yes, true. Yes, Anouk, that's true. But it's their chapters, all right? So we have different chapters than, yeah. Quit stealing my thunder, Anouk. Shh. Let's see. So I see there's some requests for later on, like page 3. Anything on the multiple choice that you want to talk about? Let's start there first, since that's the beginning of the test, essentially. 4. Oh, yeah. Okay. Yeah. 4, 4, 4. Good. Okay, so, oh, you can't see those, blah, blah, blah. There we go. So, so this is a product. And so it's not written like that with the dot there, but that's what it means, okay? So this x squared plus 1 over here, it's inside the natural log, right? It's the, what's the fancy word is argument. That's the argument of natural log. It's what natural log is operating on. This is just a factor out front, right? It's being multiplied by, okay? All right, so we need to take the derivative of this, and so we have to use the product rule, right? Product rule. Okay, then I throw my characters in there, my players. Okay, so derivative here, derivative there, right? Gotta take those derivatives. All right, so this is 2x. And this over here, I'll fill in these blues in a second, but I'm gonna pay attention to this. The derivative of natural log is 1 over the n, so 1 over the n. Left alone, right? Take the derivative of the out, which is natural log, leaving the in alone, times the derivative of the in. Okay, so that's chain rule. That's the hook-on factor out there. The chain rule says you need to, as a hook-on factor, is the derivative of the in. Okay, so that's what that is over there. So the rest of it is the same. Okay, so now I can take the derivative over here. That's actually 2x. And if you notice, this is the same thing. This is basically x squared plus 1 in the numerator, right? And that's in the denominator. So those two cancel out. right? So what you have in the end is 2x natural log of x squared plus 1 plus this 2x. And that 2x comes from the derivative. That's the hook-on factor, right? 2x. So that's your answer. And I think that's one of them. I think the terms are reversed, but that is one of them. Okay, so I don't know. What is that? E? Yeah, that is E. Why don't you add 1? We'll add 1 to what, Marie? From dividing x squared. I guess I'm not. Oh, you got it? Okay, great. Thank you. I'm like, what? I didn't get it. Okay, so let's, anything on page 2 of the quiz? More multiple choice? No? Oh, 6, that counts. All right, number 6. Okay, so what I see here is a ratio. And the stuff in the basement is to the first power, right? This is e to the x minus 1, you could do parentheses to the first power. So this is basically 1 over e to the x minus 1. Okay, so I'm going to rewrite this in an equivalent form. Okay. And so this has the potential to be that's the reciprocal function integrating to natural log of the absolute value, right? Natural log is probably how this integrates, but it will only work if this my inner function here, right? E to the x minus 1, and I'm able to, and that's the hook-on factor, right? Is the hook-on factor. So that's how I'm going to investigate over here, right? So in order to do the reverse chain rule, you have to know what the hook-on factor is. So if that is going to be my n, the hook-on factor is the derivative of that. The derivative of that is e to the x, right? E to the x, derivative e to the x minus 1 goes away. So here is my hook-on factor, and there it is exactly, right? Because this has to be precisely there, and it is. That's exactly the same expression. Not times 2, not times 5, not 1/4, it's exact. And so this is going to integrate to natural log of e to the x minus 1, and then plus your integration constant. Okay. And I guess the way to check this now would be to take the derivative of this, right? The derivative natural log of something is 1 over that. So 1 over this times the derivative of this, which is e to the x. So this is it. Okay. All right, so let's go on to page 3. So there's a bunch of them. So looks like average value. Is that what we're looking at? That's number 11. And some of you have noticed, I don't know if you look in the chat, the new section 8-1 is in Schoology. I think I posted it, I don't know, yesterday or something like that. So 8.1, you don't have it, right? Because I wasn't able to hand it to you, but 8-1 is there in today's post, or yesterday, Friday's post or whatever. No, yesterday's, right? Because when I posted the quiz, I also, I think, posted the new section. Okay, so if you haven't gotten that, you can go take a look at that there. Okay, so I think that's there. All right, average value. Okay, so the average value is going to be an integral, right, of some value, of some function. So this gives you the whole area, right, entire integral, the whole area, and you are then going to divide it up into its span, right, and how from A to B, what's the distance, what's the width of this span. So the width would be 1 over B minus A. So that's the AP. I would just divide the whole dang thing, but again, this is space saving, right? Just putting the little fraction in front. And so the average value for number 11 would be going from 0 to 2 of e to the 2x minus 2 dx, right? So that is the whole integral, but then the width of it is 2, right? How far is it from 0 to 2? It's 2. So you're dividing this integral by 2 because that's the width of it. Okay. So remember, geometrically, what you're doing is you're taking an integral, right, and you got a function that varies in height, and you are hammering it down, reworking it so it's a rectangle instead of something that's morphy, right? That does this, the top of it, you are making it so it's a rectangle with the same area. Okay, so that's what effectively you're doing here, mathematically. So this is 1/2 in front. And I have to integrate this, okay? So we have to integrate this. So that'll be easy, right? That -2 becomes 2x. So this is the part we need to think about, okay? So remember, this needs a hook-on factor, right? Because the n is right there. So my n is actually 2x, right? So the hook-on, the hook-on is going to be the derivative of 2x, which is 2. So we need a 2 here, right? Okay, so I'm going to split this up. Did I do this right? Oh, my key is wrong. Now I look at my key. See that? I'm looking at now my key. I didn't integrate -2. I think I just did the derivative of it and it disappeared. How about that? Nice job, Mr. Kuhn. So let's rework this properly. Shall we? Let's do this right. Okay. All right, so I'm going to break this into 2 integrals here. Okay, so now I can concentrate on these one at a time, right? So this over here on the right-hand side, pretty easy, right? -2x, right? We got that part there. Okay, so over here, I need a 2 in front, right? In order to have this hook-on factor be there exactly, so I need to put another 1/2 in front of that. Okay, got that? So I need a 2 in front, so I have the exact hook-on factor that I need. In order to put a 2 in front, I got to put a 1/2 out front. So I have a 1/2 here and a 1/2 here now. Okay, so this integrates as e to the 2x with that 1/2 in front. Okay, so now I still have that 1/2 all the way out in front. I need to evaluate this whole thing from 0 to 2. There we go. So sorry that I botched that on the key. So let's figure this out. Because now I have to plug these things in, right? And this is when we have to plug 0 in, because remember, when you plug 0 into an exponential, you don't get 0 out. So I have 1/2 e to the 2 times 2 minus 2 times 2. 1/2 e to the 2 times 0 minus 2 times 0. All right, so now I have a half. This is equal to e to the fourth. So 1/2 e to the fourth minus 4. Whoa, what the heck? I just lost my brain. That was weird. Minus, that's just 1/2. All right. I'm not trusting myself here because I botched this one bad. Okay, so then down here, so this I can leave on its own, but this is -4 minus another half. So this could be 1/2 e to the fourth and minus 4.5 basically, which is 9/2. Okay. Let's see. I'll put it down in a second so you can see this. So 1/2, I'll just distribute the 1/2. E to the fourth minus 9/4. So there we go. Sorry about my botch on the key. Yeah, when you integrate -2, it doesn't disappear. Yeah, that was some creative mathematics from your teacher there. Sorry about that. Let's see, Fran, is that meaning 8-1? 8-1 is being used today. Okay, so we keep going here. Okay, so I think was 12 and 13 here as well. I can't see it on the chat anyway. Oh, why did you put 2 next to the? Oh, so if I'm going to integrate this, I need to have the hook-on factor, right? Because you can see that I've got, the outer functions is e to the power, and the in is 2 times x. 2x is the in, e raised to that power is the out. So we're going to do the inverse of the chain rule. Well, the chain rule has a hook-on factor. So we have to think of what is the hook-on factor. The hook-on factor is going to be the derivative of the in, which is 2. So that's why I put a 2 out front, because I need that. That's my hook-on factor right there. Well, if I put a 2 out front, I need to compensate by multiplying by 1/2. So that's why. Then when I integrate, right, e to the 2x, right, I get this times this 1/2 in front. And the way you can check it is this. I mean, you could now take the derivative of that, and what you would get back is e to the 2x. Okay. Alrighty. Yeah, 12. Is that on there? Is that right? I thought I remember 12 from earlier in the chat. 12, 13, and 14. You guys don't trust my key anymore, do you? Okay, so what I see, well, you can't see that. There we go. What I see here is, again, a ratio, but my exponent down on the bottom is 1/2, not 1, but 1/2. So when I see that, I'm going to immediately rewrite it. Okay. So again, if I'm gonna try to use the reverse of the chain rule, I need to identify what the hook-on factor would be. All right. So I guess I've been going pink with a hook-on factor today. So let's continue that trend. Be the derivative of my in, right? Which is -2x. Well, hey, I got an x there. That's good, but I need a -2x. So to compensate, that's what I do, right? So this I need, so I have the exact hook-on factor. Okay, and then this I have to include to compensate for multiplying by -2. You can't just magically do that without keeping things balanced, if you will. Okay? Did I do that wrong too? Maybe. Let's find out. Sorry. All right. Oh, you're right, I did. I don't have a -1/2 on here, do I? Sorry. Yeah, you're right not to trust my quiz. So now when I integrate, right, this is going to be absorbed inside the n. This -1/2, not +1/2, sorry, -1/2 goes, raises up, elevates by 1, right? Elevates by 1. So from -1/2 goes to 1/2. And then in front, right, when you, we're doing the inverse of the power rule here, right? To compensate, I need a 2, right? Because we basically have a 1 in front right there, right? And then the n stays the same. And I still have this -1/2 in front. So, oh, plus C. So in the end here, those will combine, so I just have a negative. And I think, this is fine here, this is accurate, but if this is an AP question, if they give you something in radical form, they're gonna have answer options that are also in radical form. So 1/2 in radical form will look like this. The 2. You mean the -2? This one? So when I'm investigating, if I'm going to use the reverse of the chain rule, when you go front, what pops out is that hook-on factor, right? And so if we want to go exactly backwards, we have to have the hook-on factor there in the beginning, right? So, so the hook-on factor isn't going to pop out because we're differentiating. It's going to be absorbed into the n when we anti-differentiate. Okay, so we have to have the hook-on factor there in precisely, right? The exact hook-on factor. Well, you're gonna think, well, what is the hook-on factor? So the hook-on factor is gonna be the derivative of the n. This is my n right here, right, inside the radical. It's my n. The derivative of 1 minus x squared is -2x. So in front here, I had an x, right? There it is. Well, I need a -2x. And so I put a -2 there. And then to compensate for just magically multiplying by -2, I put a -1/2 out, because if I multiply these two, I get 1. And so I haven't changed the value of anything here. This is just to compensate for me making this hook-on factor be precisely what I need. I need precisely -2x. So I put a -2 there as a coefficient and then compensate by multiplying by -1/2. Okay. Oh, do you mean this one down here, the brown one? Okay, so when you raise the -1/2 to 1/2, right? You go up by 1. You got to think, okay, so what is this coefficient in front going to be, right? So 1/2 times what is going to give you a coefficient of 1, because it's basically 1 as a coefficient here of 1 minus x squared to the -1/2. There's a constant of 1 in front. So 1/2 times what gives me 1, and the answer is 2. So that's the reverse power rule part of it. Cool. Okay. All right. So sorry that I botched that as well. I'm on a roll. We'll see if I botched 13 or not. Okay, full disclosure, this one took me a while to figure out. Blah, 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 blah. You know, okay. All right, so good question. So here I was thinking, what on earth am I going to do with this one, right? Because if I take my n to be x minus 1, the derivative of x plus 1 is just 1. And that won't get me this x plus 1 on the bottom, right? And so I was like, okay, that won't work. What if I take, so I'm just trying to think, what do I take as my n, right? What do I do? And so finally, I don't know, I think I walked away from it for a little while. And I came back and said, well, what if I take this as being my n, the whole thing? That is, okay? So if that's my n, I want to know what my hook-on factor is, right? Because in order to integrate, you got to have a hook-on factor. So if I'm trying to figure out what my hook-on is, and my n is the whole thing, right? All of it, the whole numerator. The derivative of that is 1 over x plus 1. Well, my gosh, that's what that is, right? This is 1 over x plus 1, right, in the basement. So to make it make more sense to myself, I rewrote it like this. Actually, I did this right on the key, I think, believe it or not. You guys have no faith in me anymore, and cannot blame you. Okay, so this is exactly the hook-on factor, right? Exactly. Okay, so now when you integrate, you're integrating all of that. It's like that to the first power. Okay, so when you do that, that becomes second power with a 1/2 in front, because this is the reverse the power rule, and natural log of x plus 1. Yeah, and then plus c. So again, the proof of the pudding here would be to take the derivative of this, right, and see what you get, right, and you will get this back. Okay, so there's a question there. Oh, you got it? Okay. So yeah, this one took me a little bit to figure out. Yeah, I think I walked away for a little while and then came back to it. So, alrighty. All right, so let's do 14. Is that what was on the list as well? How are we doing on time? We're doing okay. All right. Okay, again, this one screams related rates, right? Related rates. So here is point P is y equals e to the x. And then that point right creates a rectangle, okay? And it says here that the point, the x is increasing at a rate of 1 centimeter per 2 seconds. I don't know why they read it like that. You can just do 1/2 centimeter per second. So notice that's a rate, right? And so this should scream at you now, related rates. Okay. How fast is the area increasing? So obviously area of the rectangle would be x times y. Okay, so that's our base equation that we're going to work from. Okay, and so I can differentiate this right away, right, with respect to time, go to the product rule here, right? But I do have how x and y are related to each other, like this. right? So instead of y, I can put in e to the x right there. Okay, x and t to the x. So now I'm gonna have to differentiate this. I still have to use the product rule, but at least now I don't have two different letters over here. It's all in terms of x over here. Okay, so now I'm gonna differentiate with respect to time. E, E, T. And I don't have time in here anywhere. So every time I take a derivative of a letter, I'm going to get a rate of change of that letter, of that dimension. Okay, so dA dt over here. And over here, I've got to do the product rule. Okay. Bend down a little bit here. Okay, so now let's do that. So I have dA dt over here. And so the derivative of x is dx dt. Right? This is just stays the same. That stays the same. The derivative of e dx is itself times the derivative of the n. Okay, so this one over here is really easy to leave off, right? You can take the derivative of x. It's not 1, right? Because it's with respect to time. So it's dx dt. Okay, so now I think it says we're looking for this, right? We know that this is 1/2, so this is dx dt, right? How x is changing. And it says when what? When x is the natural log of 2, right? So that will go, this right here will go here and here and here, okay? Right, and so I'm gonna leave it there. You just plug that stuff in, and it does simplify quite nicely, ish, okay? It does quite nicely. And actually on that one, I think my key is correct, believe it or not. Okay, let's go to page 4. You can probably do 1 or 2 more, and then we got to get to our new stuff. Or is my key so damn good on the back that, that it's okay? Or maybe you just got it on the back. Okay, well, if that's all you got, that's all you got. I'm good with that. So in general, okay, let's pause here. So this is the end of the quiz. What did you think about collaborating on Google Docs? The collaboration in general, and then specifically, how did you find the equation editor part of it? Remember, I kind of demonstrated that a little bit, the insert equation, and then you could make integrals and stuff like that. Terrible. What's that, Tomo? Which part? What was it the editing stuff, trying to type in there with the formulas, or the collaboration part? Yeah. T is debug. Okay. Got it. Print out wrap, then scan it. Okay. Got it. Kind of like what I did for my key. Typing it took so long. Yeah. Got it. Okay. Good feedback. Thank you. So if we do something like that again, yeah, maybe maybe we can think of another way to do it. Maybe we don't need a Google Doc, right? Oh, taking pictures of the work and inserting it into the Google Doc, right? All right. So thank you for the feedback. I'll take some take some hints, and I will look more closely at what you did on. I glanced at them, but I didn't like look at them yesterday. Okay, so but I will do so. Okay, so thank you for joining in and being my guinea pigs on the collaboration thing in Google Docs. Okay, so I hear you. It is the equation editor in Word. I don't know if you've used that, but that also takes time, but it isn't as clunky as the Google Docs one. I was just impressed that Google Docs even had one, to be honest with you. And so as you go forward in your careers with math or science, you're going to have to write technical papers, or even like engineering, right? Technical papers are something that you'll have to write. And it's nice to be able to put stuff in there, like a formula or an expression that looks good, right? And that's what the equation editor does for you. And the one in Word is much better. That's the one I use to format my quizzes and all that. And so that would be something moving forward that you do and own for yourself as you go forward in your math science careers. Or shoot, even if you do social sciences, you're gonna have to write papers, right? And if you make a statement, you got to back it up with some evidence. And a lot of times it's numeric, and so you'll want to be able to present it in a way that is convincing, and having things formatted nicely does help. Okay. So let's talk about our next unit. Our next unit is differential equations. And yes, it is on the AP exam, even this new version of it. Okay, and again, I'll get to that after we go over this new thing. And so this is called differential equations. Okay, that is the name of our new unit, differential equations. Okay, so differential equations. So differential kind of sounds like it's from the same root as differentiate, right? Differential, differentiate. And so really what these are, they're equations that contain derivatives. Equations that have derivatives in them. So equations that have derivatives. Okay, and you've already worked with some. Okay, so for example, let's see. Whoop. So here's an equation that has a derivative. So this is a differential equation, okay? And so what can you do with this? Well, gosh, you could go, if X is position, if you take the derivative of it, you'll get acceleration, right? If you take the antiderivative of it, you're gonna get a position equation, right? Okay, so let's do that. So let's go up. Okay, so I'm missing a key element right here. What am I missing? Yeah. Right, because basically what this tells me is the velocity of this thing, but it doesn't. So if you just know the velocity, you don't know a beginning location, right? This weekend, Saturday, went to Mount Rainier. up to paradise. Wow. All right. Because the mountain she was out in her glory. I mean, she was dominating the scene. I don't know if you've seen Mount Rainier from that close up, but it is amazing. Anyway, so drove there, right? And I can say, oh yeah, I drove 60 miles an hour the whole time. Not true. Where was I at noon? Yeah, good question, right? You need some kind of beginning you need some sort of locations there somewhere. You need some kind of information about position in order to get a precise equation. So this right here is called a general solution. Okay? This is a general solution. It's the general solution to this differential equation, right? This is a differential equation we got, and here's the general solution. If I want a specific solution, I need to have some more information, okay? So like, what if I knew, see that? What if I knew that x of 1 is -8, right? I know something that at time of 1, the position was -8. Well, now I could figure out what C is, right? I could figure out what C is. Okay, so then to do that, I would do 8 comes out, -8 comes out when 1 goes in. So is that 5? Yes, so C would be -13. Okay, so that's the general solution. So I could write now x squared plus 4t minus 13. That is called, oh, you can still see that just barely, the particular solution. Okay. And so the general solution just has, could be anything. So this would be good for any initial condition, any kind of position, this would be legitimate for, right? That's in general. But if you know something specific like this, you can find a particular solution that's customized to this, okay? And so this is really solving a differential equation, okay? So this is really easy to do because, right, we've got a derivative here that's isolated and then just one variable over here, right? So t is on this side all by itself, the derivative over here all by itself. And so this is easy to do. So all we got to do is just kind of go up. But here is what we're going to be introduced to today, because this isn't really new. I guess some of the verbiage here is new. Some of these, general solution, particular solution, that's new. But the concept's not new. So we're going to look at today, what if you have a differential equation where your variables are intermixed? So remember, the analogy here, maybe it's not a very good one, I'm going to use it anyway, would be when we used implicit differentiation to find derivatives of equations where x and y, where y was peppered throughout, right? You could have a bunch of different y's, okay? Well, what if here, it's similar, but you have a differential, you got a derivative, but you also have like x and y or x and t kind of mixed around in the equation, okay? What if that's the case? Well, you can't just take the derivative of both sides like we did here. It won't work. And so what we're going to look at today is how do you put it first into a form where you can integrate? Okay, so that's going to be the biggest thing today. Is like, how do you even do that? How do you make it so you can integrate? Okay, so we're going to use a technique called separating the variables. It's basically like, hey, x, you go over there, y, you go over there. So you go to your room, you go to your room, okay? And so you've got to get your variables on opposite sides of the equal sign of the equation, okay? So you have to use an algebra to get it there, okay? But that's not particularly difficult algebra, but it's another layer to this, okay? It's another layer. So let's do one. Let's do one. Should I do one that's in your packet? Oh, the mail just waking up. All right. Nice. That's DX. Ha. All right. So X and Y together. Oh, dang, right? And so they're all smushed together, right? X times Y. Well, so what we do here is say, okay, we got to get X's on one side, Y's on the other. Well, which side, right? There is a proper side, okay? So here's what you're gonna do. You're gonna think of this as truly being a fraction where we can separate the numerator from the denominator, okay? So what you're gonna do is you're gonna clear your fractions. Well, the common denominator would be dx, right? And so what we're gonna do is I'm gonna multiply both sides by dx. Here we go. Okay, so here's what you get. Okay, so what this tells me right now, a sewing sheet like that, do one in the packet. Oh, okay, I'll do one. Let's see, is the dx is here, the dy is there. So that means the y's have to go over here and the x's have to go over here. Okay, so in other words, if you're going to have differential on the bottom somewhere. Why? Well, because it's a derivative, right? A derivative in the fraction form is going to have a denominator. So here it's dx on the bottom. So multiply through by dx, and this is what you get. So this tells you x's go over here and y's go over there. Okay, that means I have to get rid of that y, right? So algebraically, if I want to move that y over here, I have to divide by it, right? You good with me? I have to divide by that y. Because remember, when we were doing stuff with volume or area, and we would get things that had a dy in them, and that made it so the entire equation, has to be in terms of that letter. Remember I said they're little bullies, right? And same thing here. If dx is over here, it means everything over here has to be x, right? Any letter over there. If I have a dy over here, everything over here has to be y's, right? They're small, but they're bullies, right? They make it so everything has to go their way, okay? So dx and dy on their own, when I think of them, they come from the idea of, remember delta x and delta y? Delta y and delta x, change in y over change in x. And so that's old school slope. And so when I think of delta x and delta y and moving to dx and dy, I think of limits. When you take the rise and the run and you kind of squish those 2 points together until the dy and the delta y and the delta x are smushing down to 0. It's like a limiting to 0 of delta y and delta x. So they're like razor thin height and width. That's how I think of them. Okay. And so now what do we got? These cancel. So over here, I'm going to rewrite this as 1 over y dy 4x dx. So mission accomplished. I have separated my variables. So this is step number 1, separating variables. So I got an original differential equation where x and y were intermingled on the same side. Okay, so then I have to say, well, I got to get them on opposite sides. Well, how do I decide how to do that? Well, these little differentials tell me what to do. Okay, if I got dx in the basement, I'm going to multiply through by dx. That means when I get a dx over here, everything on the right-hand side has to be in terms of x, everything on the left-hand side has to be in terms of y. So then you got to manipulate algebraically your equation till you have all the y's on one side, all the x's on the other, okay? So now that you've done that, now you can integrate. Okay, so it's like taking the derivative of both sides, but now we're taking the antiderivative of both sides. You see everything in here is in terms of x, so I can integrate. Everything over here is in terms of y, so I can integrate. Yeah, okay. So the integration of 1 over y is natural log of the absolute value of y. The antiderivative of 4x is 2x squared, okay? So now technically, both of these should have an integration constant, right? Plus c, right? But if I have a constant here and a constant here, I can bundle them into one uber constant, if you will, okay? So you only need to put one of these down. Okay, so instead of plus c and plus c, you can just put it on one side, okay? So I've just integrated, okay? I've just integrated. Okay, there's more to do, but I want to pause right here. Why did the minus change? Oh, that wasn't a minus. That was a really bad equals. That's better. Is it crazy? Okay, so the point differential equations, integrate them to get, yes, it might not be position, right? It may have no context, right? It may have no context. Like this one didn't, no context. But if you're given a derivative, you know you have one level to go up, right? If you want, okay? Okay, so the C, okay, so what we're gonna do in the end here, the solution to a differential equation is going to be a function, okay? And so right now, this isn't listed like a function, right? You got to get y equals. So there's more work to do, okay? There's more work to do. So again, the antiderivative here, the solution, the general solution here is going to be y equals something, and it's going to be a function. Yes, they just disappear. So that's what happens when we learned how to integrate before, right? Or the differentials disappear, right, when you integrate. Hold on. Mr. Wilner's cramping our style, huh? Dang. Oh, the C's don't cancel out. There's one here and one here, and I just subtract one and bundle it with this one over here. Okay. So let's keep going because we want to get y by itself. Okay. So this is if you look, a log form. So you won't always get a natural log over here. It totally depends on what the equation is here in this integral. Okay. I mean, you could also have a 2y over here or anything else, right? The reason why we have natural log is because we have 1 over y, okay? It doesn't matter, Wes. I'm going to put it over here because if I put it over here, I have to move it over here anyway. When I solve for y, right? When I solve for y, I want to get everything away from y, right? And so if I put it over here, I don't have to get rid of it. So it doesn't really matter, but it's going to end up over here eventually anyway. Okay. So to solve for y. So right now in this form, it's the log form. Okay. And so I can very easily, remember, convert it to exponential form, right? You will get equations that are not log form, that are other things, okay? And the reason, again, that I'm talking about logarithm is because that's how 1 over y integrates. That's why, okay? So that is the log form. Log form. I'm going to put it in, see if I have room over there, I think I do. Exponential form. So the base here is e, right? That's the base of my logarithm. This is my exponent. And that equals that. So all I did here, yeah, I know. This is log form, that's exponential form, right? So basically I took something that looks like log B, A, and I wrote it as B, A equals C. Right? I mean, that's what I did from here to here. Now, it's not as easy as A, B, and C, but that's the same characters. Oh, so what I want to do is get at y, right? If it's a function, I want to solve for y. And so this is one, it's the way to get rid of the log. No, now notice the log is gone now. Y is e to the base because this is natural log. Natural log is inherently base e. Yep. All right. So now I want to solve this for y. Well, do you remember what you do way back when? Well, let's see. Let me see. Don't do that now. Okay, let me hold off on that. So if I look here, I have e to this exponent here, right? I've got an exponent that's a sum, okay? So I can rewrite this over here. I'm going to keep my absolute value of y over here. This is e to the 2x squared times e to the c. Remember when you're adding exponents, it means you're multiplying with the same base? Usually we go from the same base to adding exponents, but this is the reverse. Okay, that's just the reverse. So this is another way that of pink here, writing what I wrote here in brown, using the some of the multiplication rules for exponents. Okay, so e to the c, e to a constant is yet another constant, right? E to the c, e to some random constant is still yet another constant. And so typically you won't see something written like this. You'll see it written e to the c. You could put like, I don't know, what are we going to call it besides e to the c? Some other constant. I'm going to call it b. Okay, so because it's just some other constant, that's all. Okay, if you called it c again, you're fine. Okay, so now, way back when you learned, what did you do algebraically to get rid of absolute value sticks? You remember? Plus or minus, yes. So you could write this. Okay, and so again, if you're going for a function right now, that's not a function because you got plus or minus. So you'd write this, or so that would be your general solution to that differential equation. You're like, oh my gosh, isn't that crazy? Why the b? Oh, yes. So the b is here because e to c is a constant. E to some constant, e raised to a constant is going to give you another constant. And so instead of having e to the c in there the whole time, I thought, you know what? I'll bundle e to the c and just call it b. So it just means another one. So one of the complexities of this one right here is because of this 1 over y. And because it gives you both natural log and the absolute value sticks. Okay, and so yeah, that's more to contend with, right? But not all of them give you this. And I think the ones in your book don't. Okay. No, we'll go over some, actually on Wednesday of this week, we're gonna go over we're gonna use some AP questions, okay? I would say there is, yeah, I mean, maybe part of this is, okay? But you will have, did I leave a 2x squared? Oh yeah, thank you, squared. Okay. But a lot of times you'll have an initial condition as well. Like remember in the one I did with velocity, I had a position, time, and then a location. You would have some sort of X and Y coordinate that would solve for C and then therefore B. Okay, so yeah, and so on Wednesday we're going to do like a few of these, and so you'll get a better shot at it. Okay. So let's look at one that's actually in your text, okay? You know what, I gotta pull it up. So forgive me for a second here. I gotta pull it up myself. So student text masters. Chapter 8, can you believe it? We're in chapter 8. That's crazy. Crazy. Oh, okay. Let's do example 1 that's in your text, okay? So I'm gonna write it up here and then we'll do it up here, okay? It'll be a lot easier than what we just did. You're like, it better be. So it is x plus 2y, x equals 0. Okay. Okay, so we have to determine what side we're going to put x's and y's on, right? Okay, remember that these are the things that bully us, right, into they determine for us where we're putting x's and y's. So I'm gonna multiply through by dx. Okay. All right. So do you see here? I got x dx here and dy, and so I'm going to move. I guess I'll move this one over there. I'll move this over there. So I've got now 2y dy is negative x dx. Okay. So now I have things separated, right? I got x on right side, y is on left side. Okay, so now I can integrate. And this should make you excited because there's no natural log here for this, right? So let's see, there's a question there. Oh, okay. One side is gonna be x, one side is gonna be y. That's what it is. One side is gonna be x, one side is y. And notice here, this says we're differentiating, or sorry, anti-differentiating with respect to y. I have a y right next to it. This is an x. So this integral contains nothing but x. This integral contains nothing but y. So that's why we're ready to go here. Okay. So so now let's do it. So if we integrate here, this is y squared. Integrate here, this is -1/2 x squared, and then plus c. And again, I'm putting it over here with the x because remember, I want to solve for y, right? I want to get y by itself. And so if I put the c over here, I have to bounce it over there anyway to get y by itself. Okay? So this is so much easier. So remember now, if you do the algebra and you solve for y, you're going to do this. Plus or minus. Okay? So if I write, this is what the algebra gives you, right? Right? So if I leave this like this is not a function. So it's either going to be the positive root or the negative root. One or the other. Because it can't be both, because if it's both, it isn't it isn't a function. Okay? So here are these are my general solutions right here. Okay? Those are my general solutions. Okay? So there's more questions that are on that one. So I'm going to take a look at those real quick. Is that how I started? No. I thought we had a specific solution here to find. Yeah. Well, I'm gonna pretend like we have one. Okay. So Mr. Kuhn's pretending, per usual. Yeah. So let's say I want to make sure this works okay. Let's say we know, nice, Mr. Kuhn. We know 1,4 is a solution, right? That 1,4 is a solution to this, to the differential equation. Okay, so to the, it's like it's on the curve basically. We were graphing this, it's on the curve. In general, they don't ask for general. They usually ask for specific solutions. Okay, so you have two options. You can either figure out what C is, actually, 1, -4. If you do notes, change it to that. Okay. You can plug in and figure out what C is here, or you can do it at the end. Okay. Or here, right? Which one? So I generally will figure out what C is as early as I can. So -4 squared equals -1/2 1 squared plus C. Okay. So I did that really early on, right? Right? As soon as I have a C there, I said, oh, you know what? I'm going to find C right away. So now I have 16 equals -1/2 plus C. So C would be what, 16.5, right? If I add a half. So that would be 33 halves. You can write 16.5 if you want. Okay. So now that's what C is down here, right? And so the question now is, we found C, which one of these two are we going to use and why? Okay. So one of these is going to, if you put 33 halves in here, is going to be correct and one is wrong. Anyone have an idea as how I determine, do I use the positive root or negative root? Negative. I agree. So how do we determine that? Well, here's how you determine it. I know if I put 1 in here for x, I should come out with -4. Well, if I use this one right here, if I put in 1, there is no way to get a y that's negative, because remember, a radical just gives you positive outputs. So this one here is the only way I can get a negative output, right? So if I put in 1 here, I should get out -4. Okay, so this is the one right here that will give me my particular solution. So that's your particular solution, if that is your initial condition, if that is the point it goes through. That if you know it's the solution to your equation. Okay. So typically when I'm working through these, as soon as I can, I try to solve for C. I don't know. I mean, I think if you look in the book, Gary kind of says, well, you can do it at the end. I almost never wait to the end to solve for C. If I have an initial condition, I do it as early as I can. Just because it's easier not to work with more letters. It's easier for me to work with numbers. So as soon as I get to numbers, I go to numbers. Okay, I go to numbers right away. Okay, all right. So let's see here. See if you can try one more. Where's my sheet? There it is. Okay, let's do example 3. Okay, that's on the top of page 161. Because I like it because part A and B, A is the general solution and B is the particular solution. Notice with part B there, you've got a, you know that 1, 1/2 is a solution to it. Okay, so yeah, let's do A and B, and then we'll talk about the AP exam, and then we'll call it a day. Example 3. And what page is this? 161. All right, so I got y minus 2 equals x dy dx. Okay, so immediately what I do is I'm going to multiply through by dx.
Kuhn can't see. Kuhn, we can't see.
Okay, so from this, can you see that I want y's over here and x's over here? Yeah. So to do that, I'm going to have to, I can divide
Kuhn, we can't see.
by y minus 2, and I'll get my y's over here, and divide by x as well. Right, so this is the algebra part of this, where you're just getting x's and y's on the proper side. So y minus 2
Kuhn, we can't see. Can't even hear me.
divide by x. So basically that's 1 over x. Okay, so now I got my x's over here. I got, whoa, that's supposed to be y, sorry. And I got rid of the x's over here. I got my y's over there. Oh, dang. Okay. So I'm going to rewrite this real quick so we can see it more clearly. So this was a 1 over x dx. This is a 1 over y minus 2 dy. Okay. So what I see here is I see, oh my gosh. How's that? Good thing is I'm recording. Oh, wait, it is. So here is the original one, right? This is number 3, okay? And I multiply both sides by dx. So what is what I get here in pink? So what I get here in pink tells me I want my y's on this side and my x's over here, okay? That means I have to divide by the y minus 2, whoop, to get it down there. I have to divide by x to get that over here. So this is my equation. Now that they're all, wow. Now they're separated. Now I can integrate. And so what bums me out about this is that I'm going to have natural log on both sides. Totally bums me out. You bummed out? Totally bums me out. Oh, sorry, this goes away. Sorry. And my plus C. All right. Now, you know what? I'm going to put it over here because my y's over here. And I just put it with the x's because I have to get rid of it. If it's via the y's, I got to get rid of it anyway. Okay. All righty. So notice right now, this is the first time I have my plus c. Where did the 1 over x come from? If I want to, I have to get the x, this x over to this side because my dx is right there. To get rid of this x, I have to divide by x. So if you divide by x, I get x in the denominator. So that's how I got 1 over x over here. Okay. All right. So this, what I'm going to do now is use my initial condition. It's 1/2. Is it 1/2 1? No, it's 1 1/2. Nice, Mr. Kuhn. Okay. So I'm going to use this in here, and I'll solve for c. The natural log of absolute value of 1 plus c is natural log of y minus 1/2. Okay, so I'm going to solve for c. So natural log of 1 is 0. This would be natural log. Whoa, come on, Kuhn. My gosh. Making stuff up. So natural log of, this would be -3/2, but absolute value, so 3/2. Okay. So I found out what c is. So now I can improve this equation right here. Okay. I can improve this equation here. And I'm going to move this down. Okay. So this is this equation, but with my c value. Okay. Now I want to solve for y, right? And so I'm going to use my This is log form. I'm going to use my my exponential form, concentrating on this. Okay, so natural log, right, is a base e, right, and that's my exponent is all this garbage over here. Nice exponent, right? And what does that get me? This. Woo, biggie, right? So I went from log form, again, I'm concentrating on this side right here. I'm rewriting this as in terms of exponential form. So natural log has a base e. Remember, a logarithm is an exponent. This is my exponent right here. There's my exponent. And then the remainder is right here. So the argument goes right here. Okay, so if you look over here, there's some simplifying we can do, right? Big time, right? Because let's divvy this up into e to the natural log of absolute value of x times e to the natural log of 3/2, right? When you add exponents, you're multiplying with the same base, all right? So e to the natural log of x is absolute value of x is just that, right? And this over here is just that. We're doing well here, right? All that garbage just simplified to this. Woohoo! Okay, so I'm going to put the 3/2 in front. Okay, so now let's solve for this. Well, remember to take off the absolute value sticks, we could do plus or minus. Right, and then add 2. Okay, so at this point, this isn't a function yet, right? Because we got plus or minus. Well, we can determine which one it is by our initial condition. Remember, when we put 1 in, we got to get 1/2 out, right? It's not ambiguous. When we put 1 into here, I have to get 1/2 out, not negative 1/2, not some other wonky number. So that will tell me if it's plus or minus. So let's investigate. Okay. So this is 2, and this is 3/2 over here, right? Which one is going to give me 1/2 out, right? Because I got to get 1/2 out. It is the minus, right? Oh, you can't see that. Sorry. Right? If I put 1 in here, I have to get out a 1/2. I have to, right? Because that's the initial condition. So when I'm deciding between plus and minus, plus addition or subtraction, the subtraction 2 minus 3/2 will give me 1/2. If I do 2 plus 3/2, that's what? That's 3.5, right? So minus is correct. So my final answer, my function, my particular solution is 2 minus 3/2 absolute value of x. So that is your particular solution. Woo! The big one, right? Okay. So that's quite a bit. Let's talk, I'll put the assignment up in a second. Let's talk for a second about the AP exam. It is going to be on, I think Anouk put down chapters 1 through 7 or whatever. But that's in the AP curriculum, all right? They've come up with one. And so and not chapter 8. What is chapter 8? Chapter 8 is what we've already covered. So chapter 8, the things you are not going to be responsible for is area and volume. Those are 2 big things, right? And I think we're pretty good at them too, which kind of bums me out. So those are not going to be on there, okay? Everything else, average value. We just did one today on average value. It's on the quiz, right? That's not going to be there, okay? And so that is going to be, so those things are not going to be there. Everything else is. So differential equations, what we're doing right now, okay? Inverses, right? Derivative inverse. Everything else we've done this year is eligible, okay? And so that's what I know, okay? So the things that will not be on there, everything is on there except for area, volume, and the average value stuff, okay? Okay, so that's what I'm saying. So we're going to do everything on there except for so area, volume, and what was it? Average value was all one chapter, right? That was all one chapter, and I think it was it 6? Okay, everything else but 6. Okay, and so 8 is going to be on it, and 9. We're going to do 8 and 9 here in the next little bit. Okay, lastly. Is going to be 45 minutes free response at home. And I don't exactly know how they're going to do it, but they're going to do it. Okay. There's a lot of software out there where they can record you, and you'll have to probably download some stuff onto your computer, and you'll be taking it on your computer. And again, you saw how clumsy it is typing stuff in. And so I don't know how they're going to do that, how they're going to have you type stuff into your computer. Yes, it's at home. Your AP exam was going to be at home. They haven't given out dates yet, but it's going to be at home. I know, right? So, so that's kind of the nature of it. Okay. My guess is, since it said 45 minutes and it said free response, my guess is 3 questions, right? Because on but that's what we know, that on the AP exam, there's usually 6 questions for free response, and you had 15 minutes each on average. And so since it said 45, I'm doing my division, and then doing my division, and that would be 3 questions. Okay, so that's my best guess. They haven't said 3 questions. That's my best guess. Okay, and so as we get closer, I mean, I get more information, I'll give it to you for sure. So everything but chapter 6, yes. Everything but chapter 6 will be on the test, yes. And so I'm glad that we've been doing what we've been doing, because yeah, like the stuff we just did will be on there. Like all, the exponentials, logarithms, yes, all that's on there, okay? Whole thing is 45 minutes, yes. Yep, so they have a lot of things to figure out here in the next little while, right, next little while. And so I will type stuff up and put it on my Schoology page today. Oh, and the homework. Here we go. And so there you go. So the ones on these ones down here on the bottom are review type stuff. And so now I won't have you do any more area volume stuff or average value because it won't be tested. Okay, so so that's what it'll be. I have another Zoom meeting right now with my Algebra 1 colleagues, and so that's what I'm gonna head to here next. But I will put all this on Schoology for you today, a little later on today. So with the AP stuff about the test, what I know so far, okay? Oh, you want the whole thing? Yes, I will put all of chapter 8 on there, but we're not gonna do all of chapter 8. So no, I'm not gonna do that. I'm kind of pulling some things out of chapter 8. So, so it doesn't make sense to have you do all of it, okay? All right, love you guys. And oh yeah, that's right, Mr. Templeton has office hours today. I think I put the link on there. So I mean, this DiffyQ stuff is pretty kind of crazy. So I would definitely suggest some of you, head in to talk with Mr. Temple today at 3 o'clock to do it, because again, it's, this is the, I think, the densest part that we have for the duration, right? This unit right now, not the whole unit, but this section is the densest one. Okay, so get some good practice in and utilize Mr. Templeton, because he's a great resource. Okay, I will see you tomorrow at 9 o'clock. We'll go over some of these and then look at our next little bit. Okay, see you guys. Bye.